All right, this video is another thing that looks forward to what we're going to be doing in the future, but right now it's just sort of an introduction to it. So let's start with some definitions. Let X be a vector in a subspace H where H has basis B, and this will be the collection of vectors B1 up to BP. Since B is a basis, we can find scalars C1 up to CP such that X equals C1 B1 plus dot 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 plus CP BP. This is because this being a basis, those set of vectors span H. In this case, we write, and there's a sort of an interesting look here. We write this little thing here, but then I put a little subscript of a B. This is to indicate the coordinate values of X relative to the basis B. So all that we really need to tell in a coordinate system are those coefficient values. So that's the vector for X sub B. We call it the coordinate vector of X relative to B. And the indication there is if you were to use a different basis, then you, of course, would have a different coordinate vector for X. So let's start off with a theorem. Let X be a vector in H, where H has basis B equal to B1 up to BP. Suppose there exists, let's see, CI in R and DI in R with X equal to C1 B1 plus dot 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 plus CP BP, and let's say X equals two different representations in the basis. So suppose we also have this situation going on. Suppose we have more than one way to represent X using those basis vectors. Well, the whole point of this theorem is to show that that's not actually possible when you're dealing with a basis. So suppose we have, this is true for all I. So let's say for I equals 1 up to P. Then CI equals DI for all I. So what this is saying then is there really is only one way to represent x in a particular basis. So let's go ahead and prove this thing, and there's really not much to do. You can do the 0 vector is equal to x minus x, and that equals c1 b1 plus dot 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 plus cp bp minus d1 b1 plus dot 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 plus dp bp. Well, now you're able to move some terms around, and you get this: c1 minus d1 times b1 plus dot 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 plus cp minus dp times bp. So since this is the 0 vector, remember these are basis vectors. So this means that I'll just say thus: c1 minus d1 equals c2 minus d2 equals dot 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 equals cp minus dp equals 0. This is because the vectors are linearly independent. So let's just write this somewhere. The bi's are linearly independent. That's what part of what being a basis is. All right, so then of course this means that c1 equals d1, c2 equals d2, dot 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 cp equals dp. So we only have one way. If there we can always write a vector in terms of basis vectors, and this is just saying that it's unique. So let's go ahead and put that. Therefore, the representation x equals c1 b1 plus dot 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 plus cp bp is unique. And well, let's do some examples. Here, let's let b equal -2, 1, comma 3, 1. And let's let x, the representation of x in that basis, equal -1, 3. Determine x. Well, this is not such a big deal here. Here, when we write x sub b equals -1, 3, this is telling me that x itself equals -1 times b1 plus 3 times b2. And so that's -1 times, where's b1? -1, 2. Now make sure you take these vectors in order. So many of our theorems rely on the listing of vectors in a basis being numbered from 1 to whatever they go up to. So keep that in mind. 3 times b2, that's 3, 1. And that gives us 2, -1 plus 9, 3. And that then equals 11, 2. So given the coordinate structure for the x in the particular basis we're dealing with, I'm able to go and uncover x. On the other hand, a slightly different question will be, if I give you x, can you tell me what its basis or what its coordinate vector is going to look relative to a given basis? So let's do another example to illustrate that. Let's see, my basis vectors this time are 1, -3, and -3, 5, and x equals -7, 5. I want to determine the coordinate vector for x relative to that basis. This is a little bit different. Here, what we want to do is we want to solve the following. We want to do -7, 5. In order to get the coordinate vectors, I need to find a scalar C1 and another scalar C2 such that this happens. Let me continue. C1 times 1, -3 plus C2 times -3, 5. And then, well, this is pretty simple. This sets up the following augmented matrix. 1, -3, -3, 5. I don't think I'm going to go with an augmented matrix. I think what I'm going to do is this. The reason why is I'm going to exploit the inverse that we learned for these particular 2x2 matrices last time. So what I'm going to do is multiply on the left side by the inverse of that matrix. Assuming it has an inverse. Let me check real quick. Remember on these, if I take these diagonal elements, the product is 5, and then I subtract the product of these diagonal elements, that's 9. So 5 minus 9 is not 0. That's all I care about, is that it's not the 0 vector. Then we know that this thing, not the 0 number, so then we know that the matrix is invertible. Make sure that you multiply on the left of each side. All right, on the left, I don't need to worry about a formula for the inverse because these two matrices just cancel out, and all I'm left with then is C1, C2. All the work is going to be done on the right side. I've already indicated that we have a non-zero determinant. I think your book uses that term. We won't define determinants till a little bit later, but for right now, we need to know that it's 1 over 1 times 5 minus -3 times -3. The matrix itself, remember, you swap the first and last elements like so, and then you put negative signs in front of the other elements. So once again, we have -1/4 times, I'm going to use my row column rule here. I'm going to match 5, 3 with the -7, 5. So 5 times -7, -35 plus 15 is -20. And then 3 times -7, -21 plus 5 is -16. And it just so happens that 4 goes into 20 and 16 evenly, and we end up with 5, 4. So that means that that was the coordinate representation for x relative to that basis. Let me do another example like this one, a little more complicated example, because this is the more difficult way of the two methods I've shown so far. to represent x as a coordinate vector in some other basis is the more difficult task. So let's start once again with my basis. Let's see what I have. I have -3, 1, -4. And 7, 5, -6. There's my basis. My vector x this time is 11, 0, 7. So I want to determine x relative to the B basis. And to remind you, this is what we're trying to do. I want to write 1107 as C1 B1 plus C2 B2. How many B's are there? There's only 2 of them. So I want to find the C1 and C2 is what I'm looking for. Let me go ahead and put those vectors in. C1 times -3, 1, -4 plus C2 times 7, 5, -6. Now let me go ahead and put this into an augmented matrix. The reason why this one is going into an augmented matrix is because I only have 2 equations, and what's going to happen is I don't have enough columns in my matrix to give me an inverse. So since I can't rely on an inverse, I'm going to have to take my chances with row operations instead. And you know this game. What I'm going to do right off the bat is swap rows 1 and 2. So I put that 1 at the top left corner. So I have a 1, a 5, and a 0. And then -3, 7, 11, -4, -6, 7. So I'll do 3R1 plus R2. The nice thing about that 0 at the end is it doesn't do anything to that 11 at the end of the second row. However, 3R1, so 3 times 5 is 15, plus 7 is 22. And then I'm going to do 4R1 plus R3. So here I'll get 20 minus 6 is 14. And then I'll also get, well, the 0 didn't do anything there, did it? Now I see my last 2 rows are exactly the same. So, well, not quite exactly the same. What I can do is this. Right here, both of these rows are saying exactly the same thing. They're telling me that C2 equals 1/2. So if I know that, then in the first row I have C1 plus 5C2 equals 0. So C1 equals -5C2, which equals -5 times 1/2, which equals -5 halves. This you might find very interesting. When I write my representation for x in the B basis, it's only a 2-dimensional vector, even though it's coming from a 3-dimensional space. My first thing I saw was 1/2, and then I got -5 halves. And you know, I prefer to take out the 1/2 just to make the vector a little nicer looking. And there you go. Any one of these will work. The next problem, I'm going to grab something directly from our current textbook to use because it's a graph. It shows graphically exactly what I've been doing for the last couple of problems. So let's go ahead and paste it in. All right, in this example here, what they've done is they've given us the basis vectors b1 and b2. What they want us to try to do is to show how they're related when I graph x, y, and z. Now x, y, and z are graphed using normal coordinates. They want to try to figure out what xb, yb, and zb are all equal to. So that's the indication, or that's what we're going to try to do in this problem. So let me start with x. So let me go ahead and try to figure out what xb will equal to. And then I got to figure out in terms of b1 and b2. So right here is my x. So let me see. Here's the origin. And if I go up this level to here, that is 2b1 right there. And then back here, notice that b2 is right along this right along here. It's not an axis. This is not a three-dimensional picture, even though it's kind of trying to fool me into thinking that. This is just 2 dimensions. In this first quadrant here, I have b2. Well, if I extend the same amount in the opposite direction here, that is negative b2. So let's see what we have here. Let me draw this line here. There's 2b1. And then there's b2. And you remember this little thing that we used to draw for these? What would you call these? Parallelogram rule. So if I highlight this parallelogram right here, and I can connect from 0 to x with my vector. And so that means that x is the sum of 2b1 and a negative b2. I think what I'll do is put plus negative 1 times b2 so that you can clearly see. And you know what? The way I wrote this is not correct anyways. X equals that. That's the actual value, or the actual value of x. In the b representation then, x is going to equal 2, negative 1. All right, let's go ahead and move on to y. First, we'll try to figure out what y is in terms of the basis vectors. So here we've located y. I need to expand my b's as far as I need to help. Now, it looks to me like y is about halfway between b1 and 2b1 in height. So let's call this 1.5 b1. And so that's its height. And then this length this way is just b2. So when I do this, let me go ahead and draw my little dots to indicate the parallelogram. I've sort of illustrated it here. So if I draw this too much, my lines will get way off. So then my y is going, let me go ahead and draw my y vector. There we go. So what is it? 1.5 b1 plus b2. So 1.5 b1 plus 1 times b2. So then yb will equal 1.5, 1. And then let's go ahead and move on to z. Z is all the way down here. If you were to ask me, that's about halfway. So I'm going to put this here. Let's call that negative 0.5 b2. Okay, and there's z. And then I need this b1 here. This would be negative b1. So when I look then, this here, it's hard to see, so I'm going to draw here. You can see that if you're able to see this, I'd be amazed, but my z is located right there, and that is negative 0.5 b2 minus b1. So make sure you write it in order. So negative 1 times b1 plus negative 0.5 times B2. Forgot my little b there. And then z relative to the b basis is -1, negative 0.5. Another example. This time I'm going to give you a matrix, and it will have 4 rows. So we have 1, 1, negative 2, 4, negative 2, negative 1, 0, 1, 9, 6, negative 6, 9, 5, 5, 1, 1, 4, negative 3, negative 2, negative 9. And suppose that is row reducible to this following U. I have a 1, 0, 0, 0, negative 2, 1, 0, 0, 9, negative 3, 0, 0, 5, 0, 1, 0, 4, negative 7, negative 2, 0. I want to find bases for call A and null A. So the column one is very simple. All we have to do to find bases for call A is to look at the pivot columns, and those are the guys that are going to make up my basis. Not those vectors directly, but the ones for A. So call A. Remember, if we were to call this U1, U2, U3, U4, and U5, refer back to these. So when you're doing the basis for call A, you need to use the original columns. After doing row reductions and things like that, there's no guarantee that the vectors that you get would have been in the original set of vectors to begin with. So that's why you have to use the original ones. So in particular, I'm interested in column 1, 2, and 4. So my basis then will be columns 1, 2, and 4. So call A will be A1, A2, and A4. Let me see, I need a lot of space for these. So we'd have 1, 1, negative 2, 4. Negative 2, negative 1, 0, 1. And then we have 5, 5, 1, 1. Let me give you a clue what we're looking at here. When I'm thinking of vectors for the U matrix, I'm imagining these things having zeros above them. This here having zeros above it. I'm imagining that this thing has been row reduced all the way as far as you're going to go. So above pivots you can have zeros. It's the non-pivots that you're not going to necessarily have that happen. So think about this. This vector here, I'm thinking in my mind, is 1 with all zeros. This next one is 0, 1 with 2 zeros underneath of it. And then this last vector has 2 zeros before and 1 0 after it. That way, I think of 9, negative 3 as being made up of the vector 1 with 3 zeros and the next vector 0, 1, 0, 0. That's why I can say 9 times the first plus negative 3 times the second gives me that. And I can continue too. Even when we get to 4, negative 7, 2. 4 times the first vector, negative 7 times the second vector, plus 2 or minus 2 times the fourth vector gives me this last vector. So you can see how all the other ones are linear combinations of the pivot columns. Now, for null A, it's a slightly more complicated scenario because when you go and you try to solve and set these equal to the 0 column, or you try to find the solutions to AX equals 0, this is the easiest thing to use. However, you want to clean it up and make those zeros happen like I said. If you don't, then what will happen is, if you don't, like, erase this -2, for example, then you would have -2 x2 appear in one of your answers, and that would be redundant because x2 you'll be using for something else. So when you're finding null A, your best bet is to try to clean the U up as much as possible. So put it in row reduced form. So for null A, put U in row reduced form. So let me go ahead and put my U in here, and then we'll go ahead and go through that. All right, my U had 1 0 0 0, -2 1 0 0, 9 -3 0 0, 5 0 1 0, 4 -7 -2 0. All right, and let me complete the row operation. So the first thing I'm going to do, let me go ahead and put my pivots back in here. All right, for the null A, I need to knock out this -2 and this 5. 2R2 plus R1. Now, one thing nice about working these is whatever was to the left of what I was working won't be affected by these things. I know I'm going to get this. And now let's see what else we have going on here. 2 times -3 is -6 plus 9 gives us 3. The 0 doesn't do anything, so I still have a 5 up there. And then -14 plus 4 is -10. And then, of course, I didn't affect the second row. And the third row was unaffected also. All right, let me go ahead and circle my pivots again. This time, I want to clean out that 5 up there. So I will do -5R3 plus R1. And once again, anything to the left of that particular column is unaffected just because of the way that the pivots proceed. All right, now let's see what collateral we have here. -5, so I did -5 times 2 will be, well, 10. 10 minus 10 will be, well, that's nice. And then I will leave this here and this here. All right, so now that I've got what I wanted, I've cleared out the entries above the pivots. Imagine that we have this set up like so. So then row 1 tells me that x1 plus 3x3 equals 0, so that x1 equals -3x3. From row 2, what do we get? We get x2 minus 3x3 minus 7x5 equals 0, and so x2 equals 3x3 plus 7x5. Row 3 tells me that 5x4 minus 2x5 equals 0. I don't know why that turned to a 5. Huh. So x4 minus 2x5 is equal to 0. So that tells me that x4 equals 2x5. So when I set up my solutions, notice that the matrix has 5 columns, so I have 5 variables. So we have x1, x2, x3, x4, and x5. And what was x1 equal to? Negative 3x3. x2 was 3x3 plus 7x5. x3, of course, was itself. That's one of the free variables. x4 was 2x5, and then x5 was another free variable. And one of the things we want to try to do, especially since it asked me to find a basis for null A, I'm going to rewrite this vector in the following format. Negative 3x3 plus 0x5, 3x3 plus 7x5, 1x3 plus 0x5, 0x3 plus 2x5, and then finally 0x3 plus 1x5. That means I can break this up. Let me bring out my x3 times negative 3, 3, 1, 0, 0 plus x5 times 0, 7, 0, 2, 1. So those two vectors you see there form a basis for null A. So a basis for null A is negative 3, 3, 1, 0, 0, 0, 7, 0, 2, 1. I don't know, now that I go think about it, let me go back to the first example. Did I actually write out the basis? Because I don't remember if I did or not. Ah, there it is. Now, you have to be careful here. What I did write is I should have said, right here was the statement that I wrote was wrong. I should have said a basis for column A is. The reason why is because column A is not equal to that set. Column A is equal to the span of that set. And let me go ahead and circle it. And down here, that's a basis for null A, but null A equals the span of those vectors. And so we've got the answers, those are fine, but what's more important, I think, is the ideas that are presented here. Check this out. Let's come back. I think, yeah, maybe this will be a good spot to hit it in. When you're all said and done like this, it's easy to tell pivots from other items in the matrix. So if I look, I got my 3 pivot columns, 1, 2, and 4. And I told you before, column A was identified with 1, 2, and 4. Those were my basis vectors. However, when we were solving for null A, the things that we were looking for was this, 3x3. See it there? 3x3. And then negative 3x3 is on the other side. And look at this guy right here. for the second row, an x3 appears in the answer, and so does this. So when it comes to finding null A, you're actually interested in the opposite of the pivots. You're looking at the free variables. And so basically, this vector, this tells you that x3 is a free variable. This tells you that x5 is a free variable. And look at these. x3 and x5 were the only things that I needed in my answer. So this is probably a very important thing, is when we were finding call A, we looked at the pivot columns. Well, then the columns that were left over, the non-pivot columns, we used to determine null B. So in other words, every column is either a pivot or a non-pivot. A pivot column will be used for call A. Non-pivot column will be used for null A. And in fact, a simple little note here, we see that a basis for call A consists of 3 pivot columns. The non-pivot columns tell us the free variables, and help us compute null A. Notice that null A had 2 vectors in its basis vector. So let's take a look. Call A has 3 vectors in its basis. Null A has 2 vectors in its basis. And so notice that 3 plus 2 equals 5. Well, why is that so spectacular? Of course, 3 plus 2 equals 5. Well, because the 3 comes from 3 pivot columns. And the 2 comes from 2 non-pivot columns. So all we're saying here is that the number of pivots plus non-pivots should equal the number of columns total, because every column is either going to be pivot or not pivot. Theorem. Let B1 up to BP span a subspace H. Suppose A1 up to AQ is a subset of H if Q is greater than P, then the AIs are linearly dependent. So all I'm saying is, if I have a set that spans, by taking a set with more vectors in it than the spanning set, will automatically make this set linearly dependent. In particular, if I were to take this set of B's and throw in any more vectors, then I will force it to be linearly dependent, regardless of what it is in its current state. So let's go ahead and prove this thing. For any V in H, we can write V equals C1 B1 plus dot 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 plus CP BP, where each CI is in R. This is all because the BIs span the set H. But if I remember how we did matrix multiplication and stuff, let's let B be the matrix with B1 with columns B1 up to BP. Okay, then I can write V as B times C1 dot 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 up to CP. Or better yet, why don't I just say V equals B times a vector C? So that's important. Thus, for any vector V in H, we could find a vector C in RP with V equals BC. Good. Now, since each AI is in H, we can find vectors CI in RP with AI equal to the matrix B times CI. Let the matrix C equal the matrix with columns C1 up to CQ. Remember, each I, for the i's, AI goes from I equals 1 up to I equal Q. So I should say I equals 1 up to Q for these things. So C equals that. Notice that each CI has P entries, so that it is compatible with multiplication by B on the left. The matrix B has P columns. In order for CI to be compatible with multiplication to it, we would need each CI to have P entries. Okay, now this matrix right here has P entries. Each column has P entries, but we have Q columns. So C is a P by Q matrix. Consider the equation Cx equals the zero vector. Since Q is greater than P, the matrix C has more columns than rows. We get at most one pivot per row. Some rows could have no pivots, like how we have rows of zeros at the bottom. That can certainly happen, and then you're not going to have any more than one pivot per row. So C has at most P pivots because it has P rows. However, since Q is greater than P, we must have non-pivot columns, which indicate free variables. If that's the truth, then we must have a non-zero solution to Cx equals 0. So since I have free variables, I know that I'm going to have probably an infinite number of solutions. So let U be a non-zero vector, but Cu equals the 0 vector. Now, we had each vector AI was equal to B times Ci. Well, then let me go ahead and make an A matrix where I use the AIs as my columns. So I get A equals BC. Then AU equals BC times U, which equals B times CU. And remember, that was precisely the U that made multiplying to C equal to 0. So this is equal to B times the 0 vector, which equals 0. So we have AU equals 0, but U does not equal 0. If you recall, AU is a linear combination of the columns of A. So AU equals 0 is a non-trivial linear combination so the columns of A are linearly dependent. Remember, when I write COR, that means corollary, something that typically follows easily from the theorem itself. So if A equals A1 up to AQ, this time it's not a matrix but a set, if A equals that set is a basis for a subspace H, and B equals B1 up to BP is another basis for H, then P equals Q. That means any two bases is, if you give me two bases and they have different number of vectors, that can't happen, is all it's saying. If they go by the name basis, then all bases have the same number of vectors. Let's prove this one by the theorem since B spans H. That means if B is a basis, so it spans H, Q has to be less than or equal to P, or else A would be linearly dependent. Since A is a basis, well, no, actually, let's use the theorem directly. Since A spans H, P has to be less than or equal to Q. B can't have any more vectors than A since A spans H also. So if P was greater than Q, then B, I would say, or else B would be linearly dependent as well. So when you have a situation like this, Q is less than or equal to P, and P is less than or equal to Q, you have no choice but to conclude that P equals Q. Since we now know that every basis has the same number of vectors, we can define the dimension. The dimension of a non-zero subspace H is the number of vectors in any basis for H. We denote this by DIMH. If H equals simply the zero vector, then its dimension is 0. If H equals 0, we have no basis, since the only vector in there is the 0 vector. If I take any number k times that vector, it doesn't matter what k is, I'm still going to get the 0 vector. So if k is not equal to 0, this automatically implies that the 0 vector by itself is linearly dependent. That's why we say that there's no basis associated with just the 0 space. Definition: the rank of a matrix is the dimension of call A. As a quick example, determine the rank of, and here let me see, A has 4 columns and 3 rows. So I have 1 0 0, 2 0 0, 1 3 0, 4 5 0. And of course, if I want a basis for call A, all I have to do is to look at the pivot columns, and there they are. I just got the 2 of them. So call A equals the span of those 2 vectors. This implies that rank A equals 2. Another theorem, this one actually has a name. It's called the rank theorem. If a matrix A has n columns, then rank A plus the dimension of null A equals n. That was something I sort of indicated earlier on. Let's go ahead and do the proof. So rank A equals number of pivot columns and the dimension of null A equals the number of non-pivot columns. Remember, those non-pivot columns are exactly the columns where the free variables roam. So n equals the number of columns, and that's going to equal the number of pivot columns plus the number of non-pivot columns, and then that equals the number of pivot columns is the rank, and the number of non-pivot columns is the dimension of null A. As an example, let's let A equal 1 1 negative 2 4 negative 2 negative 1 0 1 9 6 negative 6 9 5 5 1 1 4 negative 3 negative 2 negative 9, and let's say that's row reducible to U. U has 1 0 0 0, negative 2 1 0 0, 9 negative 3 0 0, 5 0 1 0, 4 negative 7 negative 2 0. So here we can tell by circling those columns we have rank A equals 3, and the dimension of null A equals 5 columns minus the 3 pivots would leave 2 left over. And this matches the equation that I had for the earlier example that involved that matrix. let A be a 5 by 7 matrix where the solutions to AX equals 0 has a basis of 3 vectors. What is rank A? Well, this isn't so bad. A has 7 columns. And let's see, 3 of the columns, so A and dim null A equals 3. That's given in the problem. So that means that rank of A equals 7 minus 3, which equals 4. An example. Show that the set V1 up to V5, which is a subset of Rn, is linearly dependent when the dimension of the span of V1 up to V5 equals 4. So one of these vectors is a linear combination of the other vectors is basically what it's saying. But to solve this then, let's let the matrix A equal the vectors V1 up to V5. Remember, rank A plus dim null A must equal 5. And now I know what rank A is because this right here, the dimension of the columns of the matrix is the dimension of the span of the, what's the dimension of the column space is exactly what they're telling you is 4. So that gives you that. So let's see, let's call the dimension of column of A equals 4. That leaves only 1 left over for null A. So thus, we have a non-zero vector in null A. Let U be that vector. Then AU equals the 0 vector. But remember, AU is a linear combination of the column vectors in A, or columns of A. So this is a non-trivial solution to that. Thus, we have a non-trivial linear combination of the vectors in A adding up to the 0 vector. Thus, A is linearly dependent. Now, you probably remember our massive theorem involving inverses. Well, I'm going to increase the length of that theorem. So this is the invertible matrix theorem continued. And once again, we're going to say let A be an n by n matrix the following statements are all equivalent to the statement A is an invertible matrix. So we're going to add, remember it went 1 through 12, so I'll increase this, 13. The columns of A form a basis for Rn. 14, call A equals Rn. 15, dim call A equals N. 16, rank A equals N. 17, dim null A equals 0. 18, null A equals simply the 0 vector. Proof. I'm going to let star 1 equal the equation AX equals B has a solution for all B in Rn. And I'm going to let star 2 equal the statement, the equation AX equals 0 has only the trivial solution. Now, those were two statements from the original theorem that went 1 through 12. I don't remember what numbers these are, but those were two statements in that list of statements for the original matrix theorem, or the original invertible matrix theorem. So what I'm going to do is I'm going to prove the following. I'm going to go start at star 1, and then I'm going to imply number 13, and then I'm going to imply number 14. Basically, I'm going to go through the numbers. And I have to fix myself here because I'm going to handle 13 separately. So I'm going to start with star 1, which is in the original list, go 14 through 18, and then back to star 2, which was also in the original list. Since star 1 and star 2 are equivalent because they were already proven to be equivalent in the original list, once I do this, I will now show that 1 through 12 is also equivalent to 14 through 18. So let's start with star 1 implies 14. These are all really quick, short things. Assume the equation AX equals B has a solution for every B in Rn. Well then, for any B in Rn, B is in the span of A1 up to AN. Remember, the matrices that I'm dealing with in this theorem are all square matrices. So in particular, the matrix A is n by n. So anyways, this equation right here says that B is a linear combination of the columns of A. That means B is in the span of the columns of A, and that by definition is COLA. Now let's go 14 to 15. This time we're going to assume call A equals Rn. A basis for Rn is E1 up to En, and we know those E's by now. So the dimension of Rn equals n. Remember, the dimension is defined as the number of vectors in any basis, which implies dim call A equals n. Now we're going to do 15 to 16. Assume dim call A equals n. Then rank A equals n by definition. The rank is defined to be the dimension of the column space, so I don't have to really prove anything here. 15 and 16 are actually the same statement twice, but I'm not going to prove 15 implies 16 in backwards because I'm going to stick with the flow that I got going. Now move on 16 to 17. Assume rank A equals n. Then we have n columns, so n equals the rank of A plus the dimension of null A. But we know that the rank A is n, so that must mean that the dimension of null A equals 0. Now we'll do 17 to 18. Assume the dimension of null A equals 0. Then null A equals only the 0 vector by definition. No basis implies that there are zero vectors in that basis. Now let's finish off this piece by doing 18 to star 2. 18, we are going to assume null A equals simply the 0 vector. Then any solution to AX equals 0 is simply x equals 0. Now finally, to handle number 13, so finally for 13 we have the columns of A form a basis for Rn if and only if. So if these columns form a basis, that means those columns are linearly independent and they're spanning. So we have two pieces to this if and only if. The columns of A form a linearly independent set. The columns of A span Rn. No proof is really needed, as this is by definition of a basis. A basis, those set of vectors are linearly independent and they span. So that was just a restatement.